All right, welcome to the start of chapter 9, which is titled Thermochemistry, where we start to transition to thinking about not just individual energies of bonds, but thinking about collections, large amounts of molecules, and the macroscopic energy changes that coincide with chemical reactions, whether that's energy we put into the system to drive a reaction or energy we get out from a system that we yield to do either some sort of work or to generate an amount of heat. So energy is this really sort of central idea to all physical sciences. And really the bottom line comes down to, if you take away anything from a general chemistry or general physics course, all things in the universe are moving towards lower energy. That's always going to be the case. The same is true with our bodies, right? When we eat food in the morning or whenever, we are ingesting molecules that have a whole bunch of energy stored up in those bonds. And we have molecular tools inside of our body as part of our metabolism that chop those bonds up in little pieces really efficiently and harvest that energy out, which we use to drive our muscles and our breathing, etc. Um, if we as humans are striving to reach lower energy, at some point we reach the lowest possible energy configuration of our bodies. What do you think that is? Well, that's when you die. Um, so all things always are striving to reach a lower energy status. And we have talked about that in several ways. I like to just draw up simple representations of that. So if we have an energy scale, I'm just going to denote that E. The favorable direction is always going to be if we start at high energy and we end at a lower energy. Remember, we're going to call that a net negative energy. We'll talk a little bit more about this perspective, negative versus positive energies, but this is how the universe works. Everything. We're always trying to go from a high energy to a low energy state. That doesn't mean that we can't go back up this, but where does that energy have to come from? Right? We have to put that energy back into the system and we have to get it from somewhere. So the image that I have to the left sort of just outlines that process. We're going to be focusing on chemical energy and how bonds and bond energy are transferred. But the bigger concept here is that energy can't be created or destroyed. It just exists. And so we can think about that in sort of the analogy of a dam where you've got, this is sort of what you learn in probably like a middle school or a high school class, where you've got a whole bunch of energy stored in the form of water that's sitting at the top of this dam, right? This stuff is not flowing, it's not moving, but it has the capacity to do work if allowed to, right? So if we open up this gate here where it says inlet and we allow this water to flow, and we have then in line a generator or a turbine, we can take the energy of the potential energy and allow that to do work on this generator, in which the energy is not, it's not being created or destroyed, right? This generator can then go to some power lines that then run to your house and they're powering your computer right now. But that energy went from the form of potential energy in water in gravity to kinetic energy in turning, literally rotating this turbine, to electrical energy that is used to power your device, to maybe battery powered energy to charge up your phone, and then you could use that phone and that energy is going to be used to power your device. You notice that when you're watching videos like this one on your phone, that device is getting warm, and so that's converting some of that energy into heat. And so the big takeaway is that all energy is conserved. It just changes form. And the same is true for chemical energy. So if you have energy in the form of bonds, we can break those bonds, but that energy has to go somewhere, either into new bonds, which some of it can, or into heat. And so thermochemistry in chapter 9 is really thinking about how do we relate those two? Chemical energy and heat energy, knowing that all energy has to be conserved. So we need to think about new tactics and principles for accounting for energy. And really, it's not going to be that different than the Born-Haber cycles that you dealt with in Chapter 6 when we were thinking about ionic bonds. We're really just tabulating up all the possible ways that energy can be transferred, and as long as we remain steadfast in adhering to this principle that energy is conserved, then it's really just accounting. We can calculate how much energy is moved in different forms. So energy within the context of this picture, or in chemical energy, is really just the capacity to either supply heat or to do work. Energy can take on lots of different forms. Even in this picture, we see sort of the potential energy of water and gravity, and so we think about this as stored energy. This could be analogous to the stored energy in a chemical bond, right? A molecule could be stable, right? Think about all the molecules you're breathing right now. There's a whole bunch of them packed into the air that gives rise to atmospheric pressure. You're breathing them in and out, and breathing them in and out. There's not any reactions going on. There's not any heat or work being done. Those chemical bonds are stable. You breathe in nitrogen, you breathe it right back out. Nothing happens. But if we can harvest the energy in that bond, that potential energy, that's sort of analogous to the water in the reservoir. And so different enzymes in your body or different industrial processes could take that nitrogen and harness energy either in the form of heat or work to convert that either into electrical energy or kinetic energy, etc. So the chemical bond is sort of the stored potential energy analogy. We could also have kinetic energy. We won't jump into this too much because it's really not the focus of this talk in terms of thermochemistry or chemical energy. But note that, as we discussed before, energy, it has to be conserved. So it can't be created or destroyed, it just gets transformed. So you can think of conservation as also transformation. It just moves from, say, a potential form to a kinetic form to an electric form, etc., depending on the actual form of the energy. And so when we're thinking about this idea of conservation of energy, we call this the first law of thermodynamics. And it's a pretty intuitive one, right? Energy can go from the potential form to a kinetic form to something else, but it can't be created or destroyed. One example of that, one of many, many, many examples we'll talk about, is just the combustion of, say, methane, natural gas in your house. If you have a gas burning stove like the one shown to the left, right, you're taking methane, which we talked a lot about in this class, which is CH4, and you are taking the energy in those bonds, right? We've talked a lot about the fact that this is a more stable molecule because these bonds are lower energy than the atoms were to start with. So what happens if we take that energy and we harvest it? That's what gives rise to this flame, right? We can burn this, we can combust this in oxygen gas, and we can yield CO2, water, and, of course, heat. And that heat is that energy that came from the bonds here that was stored as potential energy to start with, and now there's still bond energy in these, so some amount of this chemical energy was used to create these bonds, but since we went from a high energy state to a low energy state, some additional amount of energy is lost in the form of heat. And that's why or how we cook our food. Another form of energy is thermal energy, which is defined as the kinetic energy of molecular motion. So it's actually the energy imposed by molecules crashing into each other and crashing into whatever the vessel is that's holding them, whether that's a beaker or the room that you're in right now. we as humans, we sense this molecular motion, this kinetic energy, through this concept of temperature, right? We are so familiar with what temperature is to us, what it feels like to be warm or cold, but what are you actually feeling when something is warm or cold? What you're actually feeling is the energy, the kinetic energy of those molecules as they crash into your body. And so if you've got a thermometer, this could easily be your hand, whatever you're feeling temperature with, as the temperature rises, what's actually causing the mercury or the alcohol in this thermometer to rise? Well, if you were to zoom in to the molecular picture, you'd see molecules all around in this beaker or in this room or whatever you're in, and they're always in constant molecular motion. They never stop. Molecules never stop vibrating, rotating, and translating or moving in space unless you cool them down to absolute zero, which we can't do as scientists. So they're always moving. And literally, the proxy for how much they're moving is temperature. So these molecules are smashing into the bulb of this thermometer. What do you think they're doing when they smash into that bulb? What does a ball do when you bounce it against the wall? Does it bounce back with an equal and opposite force? No. Some amount of that force is going to be lost as heat to the wall, right? Same is true for the thermometer. Some amount of kinetic energy is going to smash into the wall of this. These things are going to bounce back off, but when they do that, they'll leave a little bit of their heat imposed into the glass of this bulb, which will get transferred, and it'll start to expand the density of whatever the liquid is. So when you're measuring temperature, you're literally measuring the collisions of molecules. If you were to place your hand, not on, but near this flame, above the flame, so that you could start to feel the heat of this flame, uh, what you'd actually be feeling is all the gas, the nitrogen, the oxygen, the CO2, all those things in our atmosphere that are in the room, plus probably some combustible products like water, all above this flame, and they would be rapidly moving because they have so much kinetic energy imposed by the heat of this flame, and they'd be smashing into your hand really fast and hard, such that they would start to raise the temperature of your hand. So we sense thermal energy or kinetic energy and molecular motion as temperature, which brings this separate idea, heat, to light. We need to define heat. So heat is the amount of thermal energy transferred between two objects. So hypothetically, if you had two objects, we'll just say that there are these two squares here. I've got my arrow backwards, but let's say that they're two squares and one is hotter than the other. All things will move from a high energy to a lower energy standpoint. So that means the heat, the kinetic molecular motion inside this solid object, meaning those atoms inside the lattice of this solid are bouncing around, they're vibrating really fast, they're colliding with the wall of this object, and they're going to transfer heat to the colder object. So that sort of colloquialism that you may have heard growing up, that's like, close the door, you don't want to let the cold in. That's actually the exact opposite of what can ever happen. There's no such thing as cold. There's only the absence of heat, right? Heat can flow from hot to cold because heat is a form of energy, and all things move from high energy to low. And we, as humans, measure heat transfer as a change in temperature. So we could measure a delta T, a change in temperature between these objects, and that would give us a sense for the heat transfer between the systems.